will tell us how group theory plays a role in particle physics development. So please.
Yes. This working? Thanks, Sunil, for that short but warm introduction. So, just tell me, are there limits to where I should go and not go? On the
They're tracking you with the cameras.
Yeah, okay, they're tracking me, fine. Then I can use the board freely. So when I agreed to give this set of lectures, of course, I knew that I'll be talking across to a different community, not to physicists. And when we discuss group theory and so on to physicists, generally the physicists are well up in the physics part and not so well up in the details of group theory. So today we have the opposite. I think most of you know group theory better than I do, but the physics part may not be, or the physics background, you may not be so well conversant with. So what I plan to do today is just give you the physics background and tell you how group theory came into physics and basically how it came into quantum mechanics. So I will just sort of start with quantum mechanics and then go on to build. So we'll take only the necessary things. And from the next lecture, I will talk about particle physics. Okay, so let me start with something which mathematicians like, with postulates. This is basically the language which I will be talking. Is the size okay? And it's visible in the video? Okay. So the first one we start with is to say that the dynamical state of a physical system. So this is represented by a normalized vector in a Hilbert space. So Hilbert space, linear vector space, inner product, and all Cauchy sequences lie in the space. Okay, so three things: linear vector space, inner product, Cauchy complete. And notice that I say normalized vector. So if you want a geometric picture, it only means that the directions, only the directions in the Hilbert space correspond to physical states. So that's where we start from. So here, since it's an inner product space, you can always define an angle between two states. So I'll denote the states vector as a psi. That's a state vector. So I can take psi1, that's my inner product, and divide it by the norms. Norm, standard definition, in terms of the inner product. So that's my now this is less than 1. Using the Cauchy-Schwarz inequality, you can show that this is less than 1. And therefore, in some sense, it's a measure of the closeness. Now, this is the closeness of the states, but physicists also like to call it the overlap. So we say that two states which are sort of close to each other have a small overlap. this as this goes to, so the smaller this is, the less the overlap.
Cost
So,
is the overlap in cost is large.
cos is large, yeah. One is theta. Theta is the closeness parameter, not cos. Okay. Now the next thing we got, you can also have a, let me just write it here. You could have a basis, since it's a Hilbert space. Then you take a basis consisting of psi n's. Now n can be continuous. I've taken a discrete basis, but it could well be continuous. And then I could write a wave vector sum over some coefficients psi n to whatever infinity in principle. And then the fact that this is 1 reduces to the equation Cn mod squared summed over all n, whatever it is 1. So that's my normalized states. Now, because it's a Hilbert space, the corollary of this is that you can take any state vector and it's a expansion in terms, or rather, if you take two states and you add them, it's a linear combination, then it is also a dynamical state. It belongs to the Hilbert space. So that's part of the Hilbert space. It's not really a corollary, it's just part of the Hilbert space axiom. But this result is known as the principle of linear superposition. That's the physicist language for this. Now, all right. So we proceed to the next point or next postulate. That, of course, if there's a dynamical state, but of course, in physics, we deal with dynamical variables, position, momentum, angular momentum, and such things. Yes. Yes. Natural one. You take the difference and norm of that. Yes. Is? Separable into? Sorry. How am I getting that? I'm not. I'm just writing it as a generalized notation. This could be, it could be separable in that sense, or it could be continuous. I'm just using this as a generalized notation. In fact, shortly I'll be talking about a continuous basis. So this includes both. I mean, I could write it as an integral in the Riemannian sense, if you like. So that's not it doesn't not try to send any message through that. All right. So the dynamical variables now these correspond to, note the words, linear Hermitian operators on the Hilbert space, on the state space. So those are my dynamical variables. So basically, what we want to saying is that suppose A is a dynamical variable, I put a hat on top to indicate that it's an operator, and it acts on a state psi. Essentially, it will take me to a state. What any operator does, it takes me to a different state. So there is a physical statement involved here. It says that the act of operation, act of measurement. See, what is the meaning of this? That when you measure a variable on a given state, a system is in a given state, you make a measurement on it, you get a result. But when you make the measurement, we are looking at states when the act of measurement changes the state. So this is what is happening. So the act of measurement is the linear operator. When it acts on the state, it makes it into a different state. Now you will ask, of course, that how do I do anything with a system like this? It is like trying to pick out something, and the moment you want to pick up and find out what the position is, but the moment you touch it, it rolls away. So wherever you pick it up from, it has no meaning. So therefore, now that brings us to the third postulate, which is that if psi lambda, I'll call it, is an eigenvector of A. Now, of course, we all know what that means. It means that A on psi lambda gives you some number lambda psi. Then, first of all, you see that A has not changed the vector. It gives you the same vector, and you can do it any number of times, it will still give you the same vector. Okay, remember, ultimately your state has to be normalized. So it's only the direction which matters. So here, no, yes.
So just a question that when you say dynamical variable, what's an example for dynamical variable?
I just said it: position, momentum, angular momentum, energy.
Then the dynamical state is something abstract?
It's something abstract, yes. So it is abstracts in which all the information about the state is somehow located. And the dynamical variable is something by which you pull out information about a particular variable which you identify with. That's the picture. So if you like, here is my system. And you apply with A, and out pops some measurement. Let's say A. So that's the overall picture. Now, so if this is true, then the measurement will give the value lambda. So that is the point. Now we know why we chose a Hermitian operator. For Hermitian operators, so A is Hermitian. So that implies that lambda is real. This is standard proof. It also means that the psi lambda, if you have two different psi lambda prime dot psi lambda, is delta lambda prime. So the eigen vectors are orthonormal. Okay, so why did we choose them Hermitian? Because we wanted these to be real. Because the measurement is something, as I said, like a position or energy and so on. It can't be complex. Okay, it has to be a real number. So that was my third postulate. But what is more interesting is the fourth one. So, sorry. So the fourth postulate is saying that if psi is not an eigenvector, then this will force it to become an eigenvector. Okay, in other words, you will disturb the system until it becomes an eigenvector. Once it has become the eigenvector, immediately, of course, and therefore the value lambda pops up.
Sorry, you're not saying that A prime on psi is equal to psi lambda, right? It's like the arrow
Sorry?
is equal or it means something?
No, it pushes it to psi. It's not a mathematical symbol. It's not a mathematical symbol.
Yeah, this is not
yes, it's not a mathematical symbol. I could use something else.
Okay.
So that it's clear. So it's not that it gives you this. This will happen in the physical system. So again, a simple way to look upon it is you think of a floor with grooves in it. So if there's a small ball which rolls on the floor, the ball sits in a groove. If it sits in the groove, you can always pick it up. It won't roll away. However, somewhere in between, when you try to pick up, it'll keep on rolling until it falls into a groove. Then you pick it up from the groove. So with a quantum system, it's somewhat like that. The system will sort of keep changing until it reaches an eigenstate. Okay, so this hypothesis that it goes into an eigenstate is known as the collapse hypothesis. So today I'm going to throw a lot of hypotheses at you, okay, because we don't have time to go into all the background for this. There were good physical reasons for assuming all of this, which I will not have time. And now if you keep on making a measurement, now repeat. If you repeat, there's no problem because it's now reached the eigenstate. So you will again get lambda. Keep repeating. All right. Next point is that if now, but there is a catch in it. Suppose you see the eigenvector is not unique. A system will have many eigenvectors. So which eigenvector does it go to? So here's the next part of the postulate. So if psi is expanded as Cn psi n, the probability so let's now instead of Cn psi n, let's call it C lambda psi lambda. So the summed over all lambdas. So we already have this, that this forms an orthonormal set. So that will give you a basis. All right. So therefore, that means you can also use it as a basis. So therefore, the probability, so you can expand in terms of this basis, and the probability of getting lambda is just C lambda mod squared. That's the probability of getting the measurement lambda. So obviously, suppose it's already in an eigenstate, then C lambda is 1 or delta function. So then of course you will get only 1 for that probability and all the others will be 0. But if it is not, suppose it is 2 states, it's a combination of 2 states. Then what will happen? Suppose it is C lambda is, let us say, is half and half. Then you get 50% probability of getting this lambda or that lambda. Suppose it is 1/4 and 3/4, then 3/4 of the time you will get that state, 1/4 you will get this state. So that's the probability of getting lambdas. And now,
so this number half and half for 1/4, 3/4, those are C lambda squared.
Squared probabilities. Yes. And now, of course, so what if you want to find the average value? You made a measurement of A. Your average value will simply be all the probabilities times lambda each, sum over lambda. Okay, simple. Take all the numbers, whatever numbers you get, multiply by the probabilities. The total probability is already 1. I put that here. You assume that. And this you can show is psi with the inner product of A psi. And you just expand both the size, make this expansion, use the orthonormality of the lambdas. It comes out that that's. So this result, this average value, is called the expectation value.
Angular bracket A hat psi.
No, only all operators.
No, I think he's asking that when you put the angular bracket, it's not clear in what state it is. What psi.
This one?
Yeah.
You don't need it here. A is my dynamical variable. So it is momentum P or energy E.
So, but the fact that you're taking the bracket of it,
yes,
doesn't tell you automatically what psi you're taking it in. So it depends on psi.
No. This is the, yes, it depends. It does. That's right. Yeah, that's okay. That point is important. So perhaps you could put a little psi here. Okay, that for a particular state, the average will be this. So for a different state, you'll have different C's. So you'll get a different average. Okay. Two more little things. Then number 6. So for a number 6 is that canonically conjugate. I'll explain a moment what that means. Conjugate variables do not conjugate. So I'll explain what that means in a moment. Let me get another chalk. So what I mean by that, so first of all, let me quickly define canonically conjugate variables. So these are we work in terms of, this is classical mechanics. And you have the Hamilton equations of motion, del H, del Q equals minus P, del H, del P equals Q. If this is satisfied, yeah. So if this is satisfied, these are the canonical equations of motion. Motion and Q and P are canonically conjugate. Canonical conjugates of each other. Okay. So what is that condition? So if I have, let us say, QA and PB, then that is I H bar delta AB. So let us say QA, PA, PB, QB. All right. Or we can just say PA. Both have to be satisfied. Yes. Sorry. So this is the meaning of canonically conjugate. So if they belong to that set, so X and P, X and PX, Y, PY, angular, the rotation about an angle, about an axis, theta X, and angular momentum X, these are all conjugate variables. So if this is true, now from here, what we can derive, and I'm not going to do it, but let us define an expectation value of QA over a state psi now as
here in your square bracket, those two will be what you call dynamical variables, right?
Yes. No, you're right. I should put the hat, and I should also define the commutator of any A and B. VA. Yeah. So now I define this as psi dot of QA on psi So that's this definition which I'm using. And you could do it for the squares also. QA squared psi dot QA squared psi and PB squared psi. So in that case, I can define a variance or a standard deviation rather, which is QA minus expectation QA and the expectation of that over psi. Both are over psi whole squared. No, that's right. Whole squared, which comes out to be as the ordinary standard deviation formula. Q brackets,
round brackets inside.
Round brackets. Okay, I can do that also.
When you square it before taking the acid, then you get Q squared.
Yeah. Squared. So that is QA squared. Anyway, this is the standard deviation formula. PB, which is square root of, I'll follow this carefully. Expectation of PB minus expectation PB over psi all squared. So once I define these two, then I can use this one. I'm not doing that derivation to show that delta QA, delta PB is greater than or equal to h bar by 2 delta AB. So a lot of information in this. First of all, if they are canonically conjugate, which means A and B, they're the same pair, then we have this relation. If they're not canonically conjugate, then this is delta AB. So this is greater than 0 is fine. Variance is 0 anyway. Okay. So for example, if I take delta X and delta PX, indeed that is greater than h bar by 2. But if I take delta X and delta PY, that is greater than or equal to 0, but that's trivial. Okay, so this result, of course, is known as the uncertainty principle. So we may have two more, and then this part is done. So one I have actually already used, but maybe I can. Number 6. So number 7 is the fact that this A and B have relation with the A is equal to F. That's the force quantum mechanics. Okay. In other words, for example, you wrote angular momentum. In quantum mechanics, same relation. You write on Hamiltonian as p squared by L plus some b. It will just hold two quantum. So this is known as the correspondence. Last but not least is that
Supposing I had a quantity or quantity that is and then I can write it also as p times. And if I do what just did, I get different answers. No, no, it's not for, well, you are using it on, it's just b squared by 2m plus 3. Yes. And then you put max on everything. Yeah. Something, supposing my relation was z equals 3 times. Supposing my h was b squared by 2m plus b of x times. Yeah. So when you say except for x and p, you mean except for quantities where x and p multiply. What I really mean is that you can't put equal to p equal to x. No, that I understand, but I think there's another one. The one I'm talking about, that if you have x times p, then also you can't just put that equal to. That's true. That is the ordering structure. P could depend on both x and p. Could have p or px or half x. Or anything.
Is it that the correspondence principle is saying that expectation values will obey the classical law?
There is no
So if x, p or px both will give same classical outcome.
No. That is not the correspondence. That's theorem first. It holds only in certain cases.
No,
It's
I am
not as
saying if
general.
you take expectation value x, p and px, that they can give different outcomes.
The expectation values of x, p and px.
They are different. Because if you take x, p and px, they will be plus I square.
Yeah, they have to be so by I.
This one? Alright, so you write L x is equal to
Yeah, good comparison. Not a commutation. Y p z minus z.
cross product. It's a cross product. So they're all different options. That composite.
And they all come. Well, not all, but at least in each pair they
The pair, right? We could have written. Alright, the final one is the complement line. So this is actually not equal. We need it completed itself. But then it says when a particle can behave sometimes the way, sometimes the particle. Which one behaves? Okay, so therefore, if you are looking at, for example, at an experiment like that, particles will behave as whether they are photons or electrons or protons or anything. They will behave as well. We get a free flow. On the other hand, when we look at an experiment like say, photoelectric, where electron comes, gets absorbed, and then the photon hits the particle. There you will never see the wave effect. Okay, so this is sort of physical guiding. Okay, it's not needed to do those calculations, but it's good for the interpretation of this. It really saves us. Because at every point, you didn't know which part is going, then you would be in trouble. So both these two last ones are due to both. And this one, of course, is the hadron. Now, how do I get? This one? No, photoelectric. What would be the momentum for that? Or the equation is trivial. This is a conservation energy equation with right. But to get it from first principle, this is very can be done, but it's long. You go to the real detail. So the nature of the time is different from the no. The state is the same. What you are projecting out of the state. Okay, I just come to that. let me quickly describe how to describe. So there is something position. So we follow the steps. So there is an x. X is a dynamical variable. So it's an operator. Summation, linear summation of. And let us suppose the eigenstate I call x. That's the. So let me distinguish. This x is a number. This x is a number. Real number. Its actual position. Position. Measure. This x is an abstract. Abstract. And this is a linear abstract. So of course, since it's a linear Hermitian operator, the eigenvectors. So this is really an eigenvector also. Now you see that the x's are not strict. So x is continuous and you can have all values. So this time you don't write some. So therefore, see your output and this is your normalization. Now I take an abstract size and I expand it in terms of x's. Like I've done, expand in terms of eigenvectors. So the coefficient of that I will call small psi of x. What is x? It's corresponding to sum over all x's and integrated over all x.
It is quite a physical if x prime dot x is delta, then x dot x is equal of
No,
if we just set the prime equal to the answer.
so that's basic. So this is also not quite the norm. So in this case, the norm
No, in the line above,
yeah,
x dot x is ill-defined, right? Because delta is a discrete. So if I take x in case of prime on the side, I get delta
so
of
because
zero.
they're not discrete.
Yeah, that,
So the
so therefore
product
x dot x
is
exactly not
it's an inner product density level or a distribution. So because it's a continuum, the inner products are not
so the next line is integral x of one.
it's not a so that's the sum. So that's okay. So that's not zero.
No, probably confused by a notation. X prime means the position wave function with the position eigenvalue small x prime.
Yes.
Okay. So if I replace capital X prime by capital X in the then on the right side my small x prime is small x now or
Yes, but you integrate.
huh? No, let's ask what is the pointwise value of the thing I'm doing. Then I can't no, then if it's a delta function, it has to depend on more than one.
Yeah, so this is what
It
x
has
and
to have
x
an
prime.
argument.
No, so this is some function of x and x prime.
Yeah, but I'm asking the one in the next line is not x dot x. It is x mod.
Yeah.
Not x dot x prime, but x dot x. In the integral, you have x dot x. Right? What you have called mod x squared, isn't that x dot x? Yes, yes. So it is dot with itself.
Oh.
I guess the previous line is what I was talking about. I think the integral of x prime dot. rotation. Yeah, that I agree with. So I have only written it in. That I agree with. I'm asking what is your definition of mod x squared in the next one? Huh? What is the definition of mod x? Should be extra. No, but that's not as far as what you're written. But what is this? This is not something. Yeah, so then how do you write that? That's my point. Yeah, I think it can be written, but I think the location is somehow hiding. No, but it's the same notation. The same notation. Then you go to a textbook, you will find it. Let's see that I'm missing something. I'll keep it for the moment. Let's try.
But are you saying that position eigenstates are normalized?
Yes, I'm trying to say that. So maybe that is the issue. Yeah, they are delta function normally because they are not normalized. But there are, yeah, so that is subtlety. Okay, and it leads to also this. So let's try to go ahead. I want to get so now if you use the orthonormality, then psi of x is equal to x dot. And expectation value of x. Same relation as before, but now I'm writing it. So, will come. I have the following equation. That x and that means to often we replace e hat. We are going to use only psi, then e hat of psi is minus psi. And finally x dot p. I can also use the momentum representation. I'm not writing that. Now, from here I will move on to the time evolution. So for a state, time evolution, a state yes. This one? Yeah, it's a coordinate. That isn't coordinate. And you can use other coordinates. It's just those position. So psi of p of p. What you are saying, in the time evolution, I have psi at time t equal to 0. It changes as time changes to t. And what does this? What is 0 of t? Satisfies that of t, u of t. Now, why is that? So that's the normalization. Both states will be normalized. If this is normalized, this is also normalized. Together. What does that equal to x? It
inner product. So the inner product of this is really this is nothing but I define psi of x is x, right? So this is psi. This is the momentum eigenstate. I don't know. Psi t is small. This is the psi, like an ordinary wave function. Right? The momentum. So this we have momentum.
So basically the overlap of a position and or position eigenstate to position capital X.
So class what is acting on p on I don't know such small p operator acting on the big scale. If this one can say this is an abstract vector, p is the momentum operator, and this is the momentum vector. I didn't write out the but if I had written this p I would like 12. But the time is enough. The time goes on. This is the one which is the wave function.
And is it also
linear. So constraint is secure by linear. And then what you can do is you can so that is this equation H operating on psi I H bar. This is known as Schrodinger. So from there you can find the solution for U of t. U of t becomes Hamilton two formal solution. And you can also show from here that if you have an equaling operator t, then it is satisfied by and these are equivalent plus any explicit. So basically the time derivative of an operator is the commutator. You can find by this. And for an operator, A of t will be u A of 0 u delta. So just apply this. Take the derivative from both sides, you will get this. And this is any explicit time. For example, if there is a linear term in time. This is known as the Heisenberg. We will use whatever is needed for us. Not the time. So this x dot t here. So this is something new. It does. It follows from this. So if you plug this equation in, okay, and then you plug complete set of states here, complete set of states. Like that. You can have the differential for p. And then here's the idea. Because the p, this p here is a this is a potential. So this p here is a differential. So you get a differential equation, you solve that.
If the forward time evolution in Schrodinger picture is U, then in the Heisenberg picture, wouldn't it U dagger A?
It will be, but I don't want to go into that. In that case, I'll be only doing this. I have to assume that I have to count it. So now let's talk about symmetries. So in classical mechanics, you define an action and the way the dynamic of it. UA set of UAs goes to a set of different UA prime. UA prime is a set of all the this is called a transformation of clause. Trivial example, go from paving. In that case, what happens to S? S will go to S prime. So if prime is equal to S, then is it a system symmetry. And this is a symmetry transformation. What do I mean? This is a classical but let's look at if B squared minus TIFR. So that's why I say the L. I just said that action infinity. So there could be other things. You have this, for example, and then you have a rotation. X goes to X prime R of X. And for a rotation, you know that. You know what happens under rotation? B squared doesn't change, R doesn't change, Jacobian doesn't change. So therefore S goes. S prime is equal to S. So here is a case where you have a symmetry, and rotation is a symmetry of this particular action. Where I write this recursion inside. Now, of course, if B, for example, had an unlost, so that would symmetry would not. Then I will state what is perhaps the most important result of the next part. That simply says to every symmetry there is or implies a constant on so if there is a symmetry, there will be a constant of motion or a conserved quantity if you like. If there is a constant of motion, you can guess that that action has a symmetry. And for a simple system, you can calculate symmetry for the symmetry. Also there are
need not. We also talk that in every coordinate. As you do it easily for continuous. I was one. A quantity like that, okay, where this is the 3 delta, you can just under the transition. So for continuous symmetry, you can show that. For discrete symmetry, there is a different that. So just a couple of examples. For example, S is translation integral. And a translation invariant, and we have momenta are your integrals. If S is time translation, then then triangle. And you think how well that's for the intuitive proof of another. When you go from here to here, if we say we have an why does it require to be have P as a constant? So let me come back. It's much easier in water. Okay, you can show it. I mean, the point is this. So if this is the position, then these objects are the moment. You can see there. But if their rotations is not so immediately obvious that they're angle. So when we go to quantum space, so the corresponding transformation. So did you say what was this Q1? Function only. So this is some function which can be calculated for different. Yeah. So the other inverted function. This is classic. Okay. So I have a phase function. So when it go to side side, you need a unitary transformation. That's your way. So you have gone from one state to a different state, and there's a transformation. What happens for an operator? Operator will of course be equal to U inverse, which is U. So this is going to be true for the Hamiltonian also. So the Hamiltonian will also transform as U H to that. Okay. Now I will call it a symmetry. So I give a loose argument for one. Okay? Because you see the time evolution is determined by the Hamiltonian. The time operator is equal to the IH divided. So the Hamiltonian determines how this will be possible. So now under the transform system, I get the same Hamiltonian, the evolution with time. So in a sense, the system will not change. Okay, so that's what we are going to. And in that case, if this happens, then of course I have H
equals u h u that term. Multiply by u from both sides. H u is equal to u h. And that means the Hamiltonian and u commute. So this is true only for C.
This u is not the time.
So now what happens when I take the equation for an evolution? D of u dt is I over h bar. Let's forget the debt. Let's forget the no explicit so then this is 0. That means this u of dt doesn't change with time. But can I call it a dynamical variable? No, because dynamical variables have to be Hermitian. This is unitary. However, there's nothing to stop me from writing u as e to the I some real number into some g. For this g now is and if this holds, you'll also get h equals 0. And now dg now what is important? The eigenvalues of g are there. Okay, g in principle could be a dynamical variable. So g is a possible dynamical variable. Eigenvalues are real. And g doesn't change with time. Eigenvalues do not change with time. Okay, so they are there. So they are constant. So that is the Noether's theorem. That if you have a symmetry, which means that the Hamiltonian is unchanged like this, the eigenvalues of that e to the I. Okay, that corresponding. So I'll use the standard word for it. We'll link up in the books. So that Hermitian generator that has eigenvalues are constant. So that's very good. Fine.
Just one question.
Yes.
So, but in quantum mechanics, all symmetries need not to be unitary. They can be anti-unitary. But that will lead to conserved quantity or it will.
The transformation of the wave function. And you probably know this thing. The one we encountered is generally time reversal. And then you keep the one more, which is that the symmetries of H one more group. This one is to this link up. So that's very simple because what do we need for a group? Let's say you have U. You have a state psi. It goes to a state psi prime. Let us see U1 into psi. And then you have another state, the psi prime, goes to some other state psi prime. This is U2 into psi prime. So that is equal to U1 into psi. So effectively, the psi double prime is U2 U1. So that's the result of two transformation. That's a composition. Now, this composition I need to prove that it forms a group. Okay. So what are the things I need for that? The most important one is closure, because the others are sort of different. What are the others? You can always like linear operators, they satisfy associativity by identity. Identity is you take the identity transformation, don't do it. Psi remains itself, identity exists, and therefore since this is unitary operating, you would either respect one. So the other three are trivial. Only one to check is this one. So H, and it's transformed with U1 U2 and U1 U2. That. So that of course now is U1 U2 is associated to two data U1 data. So if I put this bracket, the answer is this is H U1 data. So that is the satisfied closure. So therefore, if I have a set of on the group, it will satisfy closure. And you can also similarly show that H of G1 G2 to work with generators. So I'm putting hats on these because these can be dynamic. So that of course is G1 times H G2 plus H G1 into G2. Now each of these is stuff. In other words, the connection with quantum mechanics comes that if I have symmetries of that, then I get constants of motion. Conversely, there are constants. There must be a symmetry. So therefore, suppose I'm right looking at and I don't know anything about it. It's too small to be seen. So I can make a model. But what guides me is I look for conserved quantities. If there are conserved, then I say, okay, system. For example, if it looks like angular momentum, I look at the spectrum, shows me something like angular momentum. Then okay, that means the system is rotational. I go back and so let's see that only something is concerned, maybe angular momentum particularly. So that rotation is others are not, and so on and so on. And this has been the main tool for deriving theories of art. We have looked at, and I'll talk about that. We've looked at particle behavior, and from the particle behavior, there are certain number of particles. There's a conserved quantum, there is a symmetry. If there is a symmetry, there is a so, and that's why group theory in trying to construct things. So, eigenvalues. So I wrote that somewhere else now. So it's the best. Yeah. No, I did. So okay, I haven't written it actually. So the constants of motion are sometimes called good quantum. Good because this whenever you do the experiment, once you change time of course, you do it. So the good quantum numbers, constants of motion, conserved quantities are all. Okay. To that question, how do we know that I wrote on another indent. You have translation invariance.
You have, let us say, x into x plus x. So what is happening to the psi? Let us say psi of x. Psi of x will become psi of x plus x. So psi plus of x plus epsilon del x of psi. You can write that. You, it's a very simple minded code. You can write it as plus I times I over e power epsilon times minus I. No moment. So this is I of x plus I over epsilon. The momentum of now so similarly, you can see for rotation, this corresponds to the angular momentum. If you get the time density, it may be. So that's the simplest way. Also ask the question that people see outside. See outside question. Are there any questions on the room audience? Okay.